Hello, everyone. Anybody have any questions before we get cracking? I'm sorry about shining up just that time, but we do have a little bit of time to answer questions. Nothing. We only got 4 of us in here, though. That's not very good for, especially being started a little late. So this, I guess we'll just go on. This chapter we're in is chapter 10. We're going to go ahead and knock that out for tonight. Basically, you can check out some other videos if you need some stuff. I'm going to skip a few steps. Normally, I'd like to take the time to derive all these equations and all that stuff, but so you can actually see where it came from. Basically everything that we're doing is coming from differential equations, and they're not differential equations that you can't do. I mean, you can look right at your book in chapter 10. You can see they're pretty trivial to do. They're all well, some of them are sort of like what we did when we studied projectile motion and actually added in wind resistance. And then, well, one of them's like that. And then all the rest are just like chapter 14 when we did not the wave equation part, but when we did like the pendulum and mass on a spring, that sort of thing. So they're fairly straightforward. But basically, now that I've covered how to calculate the self-inductance, or L as we labeled it, the inductance itself. Like I said, most people do not call it self-inductance, but either ways, we'll call it inductance, the thing measured in henries that's only about 1 coil as opposed to 2, which is mutual inductance. So now that we've done that, what we want to do is we want to see how those things behave in a circuit. We already covered, for instance, resistors in a circuit. That was sort of the, actually, I think that might have been the second thing, oddly enough. And the first thing we did was capacitors. So we now have capacitors and resistors, but now we're going to introduce inductors. And what you're going to see is capacitor and inductor are very similar, but they're also in some sense opposite. Specifically, the capacitor ends up storing its energy in an electric field, and the inductor ends up storing its energy in a magnetic field. And we end up having basically a lag between the voltage and the current in those devices, whereas in a resistor, the voltage and the current are in phase. What do I mean by that? Well, I mean, we're talking about sine waves as the AC current goes. And you could say, for instance, maybe the current is a sine wave, but the exact same voltage would be a cosine wave. So it's off by 90 degrees. Or it could be actually what it turns out to be. In one case is we have a cosine that represents the current, and in the actual, and make sure I'm remembering this correctly or saying this correctly. So in the case of the capacitor, we use this phrase ICE, and that means the current leads the voltage in a capacitor. So the voltage turns out being, instead of the current, which is cosine omega t, the voltage turns out to be times cosine omega t minus pi over 2. And then the voltage in an inductor turns out to be cosine omega t plus pi over 2. So it's ahead by 90 degrees, whereas the capacitance is behind by 90 degrees. And then the resistance, the voltage through there and the current through there are both in phase. So that makes them behave differently, so that, basically, when one has a large voltage across it, another one does not have the same voltage across it. And in fact, when you add up the voltage across the resistor, the capacitor, and the inductor, they add up often to way more than the voltage of the system. So that's kind of a neat effect. You have to take that into account, for instance, if you want to talk about how much power is being dissipated or all that sort of stuff. So I now have 7 people, 7 people in the classroom. So I guess that's good enough. We'll get started. So I'm going to jump right in. And for instance, I had done previously the inductors, and we talked about the energy. We calculated the actual inductance for a solenoid, all sorts of good stuff. Oh yeah. So what I want to do is start off, I guess, with this. I actually took notes this time so I can make sure it would be nice and neat and I wouldn't miss anything. So let's go ahead and get started with basically an LR circuit. I think is the first one I want to do. Let me double check. Yes, an LR circuit. Okay. So with an LR circuit, I'm going to draw it for you and we're going to share the screen. So let me start by sharing screen. Feel free to ask me questions at any point. And this is probably going to be the only one whose differential equation I actually solve. I'll leave the rest to your textbook author. And feel free to ask me. In fact, you can also look on my Facebook page, on my YouTube channel, and you'll see various times where I've derived that in the past if you'd like. Just do a search for LRC or inductor, or do a search for capacitor, and you'll find all sorts of videos. So let's start off with drawing the actual circuit. So for instance, in an LR circuit, we're going to have, as the name suggests, basically an inductor and a resistor. So with an inductor and a resistor, basically what it's going to look like is we're going to have a power source, which is just a battery. And that's going to have a voltage V0. But next to that, of course, is going to be yet another wire. And then what we're going to have is a switch that can go from either wire by going through this little arc right here. And I'll say the switch sits right here right now. Now this wire is going to go back, go up, and run into the resistor, which has a resistance R. And then it's going to run into the inductor. And notice the symbol for an inductor looks just like a solenoid, because a lot of solenoids are, a lot of inductors that you use in the circuit are literally just a solenoid. So you take a solenoid, sometimes they'll have a piece of metal in it, sometimes they'll just be empty tubes, stuff like that. And then sometimes there actually be a torus, where you literally take a really long solenoid and you bend it in the shape of a donut, and inside the donut would be like an iron ring or something like that. So that's our circuit. And when I close the switch, and by that I mean when the switch goes over to connect to the battery, we can actually use Kirchhoff's loop rule. And Kirchhoff's loop rule says basically that the battery V0 is a voltage increase. So if I start to the right of the battery, then that's a voltage increase of V0. Then I go through the switch and I hit the resistor, and the resistor, of course, since I am going in the direction of the current, which is that right there, will be a minus I times R. Now, also from Faraday's law, we learned that the voltage is going to be negative L di dt, so that's going to be a voltage drop as well, and that voltage drop is going to be L di dt, and then we're back where we started from, so we can write that as 0. Now it turns out that this is fairly straightforward. This is almost identical to when we solved the projectile velocity for a drop body with actual air resistance. So in that case, the body was being pulled down, or the mass M was being pulled down by a force mg, which is his weight. But as it sped up, a drag force got larger and larger, and that drag force, of course, was some constant B times V. So as the V got larger and larger, the BV got larger and larger, and that was pointing in the opposite direction of MV. Eventually, you come to a point where mg is equal to B times V, and at that point, the velocity stops increasing, and you have terminal velocity. Well, that differential equation that we had from that turns out to be solved just like this one. So what I'm going to do is I'm going to start off by writing L di dt on one side. So I've pulled that over to the right hand side, say, but then I flip the sides to make it the left hand side for some reason now. I don't know. Okay. And then on the other side will be V0 minus I times R. And this I is actually, as you can see by the derivative, is actually a function of time. So what I'm now going to do is I'm going to divide both sides by V0 minus IR, and then I'm going to multiply both sides by dt over L, and that will give me, in fact, di over V0 minus IR is equal to dt over L. Now I'm going to say let U equal V0 minus IR, then du is going to equal negative R times di, or the way I like to do it is di is equal to du negative over R. So I got that now. I'm going to pull the negative and the R that comes in the place of the I of the di. I'm going to place that over with the dt. So now I get the integral. Actually, I should probably go back to the red, even though I didn't care for writing in red. I just started it. So I've got the integral of du over u is equal to the integral of negative R dt over L. I'm going to integrate this from t equals 0 to sometime t, and I'm going to integrate this from I0 to, I think I'm going to integrate that from I0. Yeah, that's what I'm going to do. I think I'm going to integrate it from I0. No, I don't think I'm going to integrate from I0. Let me see. Yeah, we'll leave that be right now. That's what I'll do. Yeah, from I equals 0 to t. The reason why I was, from I equals 0 to I of t. The reason why I was thinking is I was remembering the problem I'm getting ready to work on one of the first questions. I'm actually giving you the answer to it when I write this down. So I was thinking, I don't remember doing that, but clearly I did. So the integral of du, I think you all know, is just the natural log. And then it's going to be the natural log evaluated at I of t minus the natural log evaluated at I equals 0. Of course, that's with u, which is V0 minus IR. So when I do the evaluate the natural log at I of t, that becomes the natural log of V0 minus R times I of t. And then when I evaluate the natural log at I equals 0, it just becomes V0, the log of V0. And of course, you're going to subtract those logs. It'll be the log of parentheses V0 minus R times I of t minus the log of just plain V0, and a difference of log is equal to the log of the quotient. So in this case, I'm going to get the natural log of V0 minus R times I of t. And again, that's just reiterating that I is a function of time. That is all going to be over V0. And this side is just going to be really simple. It's going to be negative t over, now I'm writing this way for a reason. It's going to be over L over R. And in fact, we're going to introduce this time constant, tau, which is called L over R. And if you work out the units from that, you will find that, in fact, and this is a good exercise, you will find that the units of tau are indeed seconds. Okay. Now, I would like to solve this for I of t, so I have I as a function of time. So what I'm going to do is I'm going to raise e to the left-hand side power. And then I'm going to raise e to the right-hand side power. And I'm going to set them equal to each other. And of course, once you raise e to the power of natural log, the argument of the natural log is the answer. So that's going to give me V0 minus R times I of t over V0 is now equal to e to the negative t over tau, which is a little easier way of writing it. If you fast forward a little bit and do some of the work, basically I'm going to have to multiply both sides by V0, and then I'm going to add R times I of t to both sides, and that'll give me, and then I'll pull the e to the negative t over tau to the left-hand side, and basically what I'll end up getting after all this work is that I of t, and I do recommend you do this algebra. It's not hard at all. I of t is going to be equal to V0 over R times 1 minus e to the negative t over tau. Okay, so that's what the actual current as a function of time is. And in fact, if you were to graph that, what you would see is that this would be, say, time, and this would be current. And what would happen is the current would rise up and sort of asymptotically approach V0 over R, which is sort of what we expect, because once the current immediately starts flowing, that goes from no current and no magnetic field in the inductor to a current. And in fact, it's going to try to climb up really quick. And in doing so, Lenz's law is going to kick in. That's going to create a back EMF in the inductor. And the inductor, in fact, is going to act like a battery fighting the existing battery. In other words, it'd have positive towards the positive. So it's trying to make a current going counterclockwise when there's actually a current going clockwise. That's going to slow down the buildup process. And as that change in current gets smaller and smaller, you're going to see that the inductor's role becomes smaller and smaller as well. So it'll just limit itself, and then eventually it'll stop changing completely, in which case the circuit will just act like a circuit with just a wire and a resistor, because once the current's not changing, then the inductance doesn't create an EMF. Yes, Michael?
Why, back when you were doing the integral, why is it natural? Why is it divided by V naught?
Because that's where you're going to take the natural log of u for the first part of the integral, because you remember you do the top range, the I of t. Well, that's V0 minus R times I of t. And then you're going to subtract from that the natural log when I is equal to 0. But if you take u when I is equal to 0, you see that that's just V0.
Oh, okay. All right.
That makes sense?
Yeah.
All right. So yeah, that's going to fight this thing from going up, and it looks like it asymptotically approaches that particular amount of current, which again is just the current you'd have if it was just a battery with a resistor. Okay. At that point, once current isn't changing, then we know L di dt is 0. So you don't get a change in voltage other than what's due to the resistance of the wire itself. But that's actually how that happens, and it actually doesn't take very long. It's usually 2 or 3 time constants, which is what tau is, before it really reaches a number that you cannot tell is different than V0 over R. And in fact, the way this logarithm works is you can see that at, say, t, all right, time tau, say, this comes up here, goes over to here, and that 0.63 times V0 over R. In other words, after one time constant, it should reach about 63% of V0 over R. So that gives you a little bit about the significance of tau as well. Now, once you have that circuit going, you can take the switch and turn it off the battery. And if that happens, then what's going to happen is the battery isn't going to be there to run the current anymore. But as soon as the current starts to decrease, Lenz's law is going to kick in, and the inductor is going to start acting like a battery, pointing in the same direction this time that the original battery was. So it's going to try to create a current in the clockwise direction, whereas before it was trying to create a current in the counterclockwise. So that's going to actually fight the current from dropping. And in fact, what you end up getting for that one is basically another Kirchhoff's loop rule. So I can write, let's say, red, Kirchhoff's loop rule for the switch being open. We're basically just going to have a current running through a resistor and into an inductor like this, and then it just goes through a wire. because the battery has completely been cut out now. Okay. So when that happens, what you ultimately see is that negative L di dt minus 1 over, or excuse me, I was thinking I had a resist current there. I mean, a capacitor there, minus IR is equal to 0. That, in fact, gives me a differential equation that's actually pretty straightforward to work with. It becomes L di dt plus IR is equal to 0. That, of course, you can play with and write out as di over I is equal to negative R over L times dt, or times dt. Okay. So you can see how that works. Notice this dt is the same thing. This negative R over L dt is the same thing as dt over tau. Like that, because tau is L over R. So now when I integrate that, I get the integral of di over I is equal to the integral of negative dt over tau, which is a constant. And that gives me, I'm going to integrate from I0 to I of t, and I'm going to integrate from t equals 0 here to t. So that's just going to give me the natural log of I of t over I0 minus negative t over tau. Again, raising e to both sides, to the left-hand side's equation, and then raising e to the right-hand side of the equation power, setting those equal, will ultimately just get I of t is equal to I0 times e to the negative t over tau. And that's another expression that's useful, and we're going to use that quite often. With this case, you're going to get, again, a current starting this time, instead of starting at 0 like it did the previous one. In this case, it's going to start at I0, and it's going to exponentially decay. And now you would actually have that tau, one time constant later, is going to be 0.37 I0. So it's dropped down to 37% after one time constant. Okay. Again, the same time constant exists. Tau is equal to L over R for this type of circuit. So that's the stuff that you sort of need to know from this part. But all of this really is trying to get you to see how capacitors and resistors and inductors all interact. So now that we have these basic equations, let's go ahead and solve an actual physics problem with it. So for instance, I'm going to take, I want to take an LR circuit example and solve that for you. So this is not unlike the ones that the book gives you. It's almost identical. In fact, we'll say basically we initially have a 20-volt battery. So the battery V is equal to 20.0 volts. And it's going to be connected to a 240 millihenry inductor. And that's going to also be connected to a resistance of 60. Actually, let me make that 3 sig fig, 60.0. I'm going to put a dot there too, so we could read that 240 as a 3 sig fig number. And we'll have a resistance of 60.0 ohms. And what I want to know is A, what is I when the switch is closed. So in other words, the instant the switch is closed. So I'm going to say I, E, in other words, at t equals 0. Part B, I'm going to ask for how long will it take the current to reach half its max. So at what time will I equal 1/2 of I max? And of course, with that comes the question of what is I max, but I think you can probably tell all the way from the graph or from the words I've already said. So there's my part B. Part C, I'm going to say what is the maximum current? And part D, I'm going to say what is the time constant? In other words, what is tau? And part E, what is the rate of energy being delivered by the battery? In other words, I want to know what the power of the battery is when I is equal to 1/2 I max. In other words, at that time that we pointed out in part B, how much power is being created by or being delivered or used per second. I actually noticed, as I said power, I shouldn't say per second, but anyways, how much energy per second is being used at that time. And then F, using our information that we know about inductors, we want to know at what rate is energy being stored in the magnetic field. So at what rate, again, that's a key word for power, is E, the energy stored in the, got ahead of myself, in the B field. Okay, so that's our questions here. Let's do our solution. Okay, so what I know is that I of t is equal to V0 over R times 1 minus e to the negative t over tau. When we first close the switch, this is the equation that accurately treats our current or accurately reflects our current as a function of time. Okay, so for part A, you can just look at t equals 0. I of t equals I of 0 is just equal to 0. And we know that because if I put a 0 there, that becomes e to the negative 0 power, which is e to the 0 power. And anything other than 0 raised to the 0 power is 1. So e to the 0 equals 1, which means inside those parentheses you have 1 minus 1, which is 0. So we know that way, but we also just know it from the physics of the situation. It's going to take a finite amount of time for current to flow. Obviously, it's you can't really decide how small of a time interval it is, but you know it's not 0. Okay. Any questions on that part? All right, with part B then, I don't see any raised hands. In part B, I want to know at what time will I equal I max? Well, if you look at that I as a function of time, you could take the limit of that I as t approaches infinity. And basically what you'd see is you've got V0 over R times parentheses 1 minus the limit as t approaches infinity of e to the negative t over tau. So that's the same thing as the limit of 1 over e to the negative, or excuse me, e to the t over tau. So as the e to the t in the bottom allows t to approach infinity, then that becomes basically 1 over infinity, which of course is 0. So you get V0 over R is the maximum current you'll ever get. So I max is actually just V0 over R. So I want to know if I set I of t equal to 1/2 V0 over R, then my equation becomes V0 over R times 1 minus e to the negative t over tau. Now, you can automatically see that the V0s drop out there. And you could also see that now we're going to have 1 minus 1/2 is actually equal to e to the negative t over tau, and that t is the t that I want. So what I'm going to do is I'm going to say this is 1/2 is equal to e to the negative t over tau. I'm going to take the natural log of both sides. The natural log of 1/2 I happen to know is negative 0.693. And the natural log of e to the negative t over tau is just going to become t to the negative t over tau, or excuse me, the negative t over tau. So the left-hand side becomes negative 0.693. That also means, by the way, that the natural log of 2 is 0.693. That's just something I've always known since I started learning about logarithms. And again, whenever you take the natural log of its base, whatever its base is raised to, that power becomes what's left. So now I've got that equal to t over tau, like that. So we can see that t is going to be equal to 0.693 times tau. And that's actually a correct answer. But in order to actually know the number of seconds or milliseconds, we really need to compute what t is, which is part C. No, it's part C. So I'll go ahead and put part C here. And tau is actually equal to L over R. And that is, in fact, 240.
That's part D.
No, I think you're misreading it. Yeah, oh, gotcha. Yeah, you're right. That's right. Sorry. I was actually asking for my max, and so yeah, you're right. Exactly. Thank you for correcting me on that. I was like, no, you're crazy, man. All right. So yeah, let's go ahead and put that as part D then. Okay. So I'm going to go ahead and do part D, which is basically 240 with a decimal point after it, millihertz, millihenries. And you'll see there's a way you can actually keep the prefixes, milli, nano, micro, that sort of thing. And we do this a lot in electronics. So I'm going to show it to you here. I think I've showed it a couple times before, but 240 is going to be divided by 60.0 ohms. And if you look at the henries, you can see that basically, well, you can figure out how the henries matches with the ohms to get seconds. So 240 divided by 60 is obviously going to be 4, or excuse me, that's the same thing as 24 divided by 6, because the zeros cancel out here. So I can cancel out that 0, I can cancel out that 0. Now I just got 24 divided by 6, and 6 goes into 24 4 times. So in this case, I get 4.00 milliseconds because I didn't cancel out the milli. Well, what really happened? Well, we know, for instance, that V is equal to negative L di dt. So from that, we can figure out that the unit of L must be this is di over dt, sorry about that, must be volts times seconds per amp. Let's write this a little bigger so you guys, or at least look at it a little bigger so you can see it. So that's going to be volts that we had over there already. And then that's going to be times seconds. And then that's going to be divided by amps. That's what's going on there. And let me fix this god awful looking derivative here, because that was just really ugly. So that's an equation we could use to make sense of it. You can then see that L over R in units is going to be volt seconds per amp. And then at the bottom, you're going to get an ohm from that. And of course, if you look at V equals IR, you see that ohms is volts per amp. So this quantity right here, volts per amp, is equal to ohms. So that ohm is going to cancel out with this ohm, and you'll get just seconds. So that's how the units worked out on that. And now we've got another answer. This one's actually, let's undo that. This one is equal to tau, and it's of course part D. So I'm going to circle that, and luckily a student caught me using the wrong label. Okay, so now I can multiply 0.693 times, if I can find my calculator, times 4. Obviously it's going to be about 2.5 something, but 0.693 times 4 is 2.77 2.772 with one extra sig fig, so I'm underlining it, milliseconds is equal to T. And I'll write that as T 1/2, meaning the time required for it to get up to 1/2 of its max. Okay, so now we've done A, B, and D. I still got to do C, of course. Now, I've already explained to you what C is, specifically the I max. So now I can just go ahead and calculate it. I really have a hard time choosing to stay in green, evidently. So I max, as I argued from the limiting process, is actually equal to the limit as T approaches infinity of V0 over R times 1 minus e to the negative T over tau, which I think you can see is basically 1 minus 0, because the limit of that e to the negative T as T approaches 0 is going to become 0. So you just get V0 over R. What we know is V0 is 20.0 volts. And R is, of course, 60.0 ohms. So I'm going to say I max is clearly 0.33. Ooh, scratch that. It's yeah, that's 1/3, right? Yeah, 2/3 or 2/6. So that becomes 1/3. Yeah, 0.333. I saw the 2 there and the 6 there for a second. I started thinking it was 6666, but it's not. So that's going to be the actual answer, and that's actually in amps. So you're talking about 333 milliamps roughly. Any questions on that part? Notice how this is why I often don't work a lot of these problems. These are pretty straightforward. Other than this part you'll see in part F, these are pretty straightforward, just plug and chug formulas. But still, every now and then I just like to show you some of these parts so you can understand how it's worked, because otherwise it just looks like really scary theory and you don't really get any applications. So now I'm going to go ahead and do, since I already did D, I'm going to do part E. And part E is what is the power of the batteries delivering at the time, which we determined was 2.772 milliseconds. So now I'm going to calculate what is the actual power from the battery. Well, the power from the battery is going to be equal to I for the that the battery supplying times V that the battery supplying. Okay. In this case, we know the current is actually going to be the 0.333 amps. So I'm going to put 0.3333 amps times the voltage, which as we know is 20.0 volts. And if I multiply 20 times 3, or 20 times 0.333, which would actually would have been easier just to divide by 3. That's 6.66. $6.667 watts. So that's the power delivered by the battery. Any questions on that part? Dang, somebody just ran over my mailbox.
Are you serious?
Yeah. My dog was barking because somebody came to the door to tell us they just ran over our mailbox. I live in a back street. How the hell do you run over a mailbox? Oh, well. All right, back to class. So here's F. F is a little bit more tricky. What we got to figure out is at what rate is the electric energy stored in the magnetic field in the inductor. And basically what you got to realize is when they ask for the rate of energy, they're really talking about power. Power is, one way of writing it is power is dE over dt, where E is the energy. You could also write it as dW over dt because sometimes the energy comes from work. Or you could write it as du over dt because sometimes the energy comes from potential energy. But generally it's just dE over dt. So now I'm going to write for part F, the power in the magnetic field, which I'll subscript B, is d by dt of E. Okay. Now, in this case, we actually, yeah, I'll do that. Well, I did use potential energy before, so it might be a little less concerning if I introduce it that way, because you can look back at your notes and realize, oh yeah, that's right, Mr. Younger calculated U before, and what U was I times LD, or excuse me, hold on a second. It's d by dt of, in this case, we had I times L, if I remember correctly. Yeah, that's what it was, I times L. Okay. Is that right? No, that's not right. Oh no, we had I think I had 1/2 Li squared. That's what it was. Yeah. So let me kill that. Sorry about that, folks. I was just trying to remember. So the potential energy was 1/2 L times I squared. Remember, that was the formula I told you was just like 1/2 CV squared. So what I'm going to do is L is a constant. So that's going to be 1/2 L coming out front. Then I'm going to take the derivative of I squared with respect to I times the derivative of I with respect to T. That's the chain rule, in other words. So I'm going to get, notice the derivative of I squared with respect to I is just 2I. So that's going to cancel out the 1/2 in front. And now I'm just going to get L times I times DI dt, which I can also write as I times L di dt. Now, there's a couple ways you can do this. For instance, in my lecture, when I was demonstrating this, I just took the I as the 0.3333, or excuse me, no, the 1/2 of 0.3333. because we needed to know what the current was at that particular point. Remember, they're asking for the power delivered when I is equal to 1/2 I max. I max is 0.3333. So that's basically what 1/, well, it's 1/3 is what I max is. So this would be 1/6, and 1/6 is 0.166666 or whatever. So anyways, you can do that, put that in I. L is the actual inductor, the 240 millihenries, and then DI/dt is just the derivative that you get from looking at the expression for I, which is V0 over R times parentheses 1 minus e to the negative t over tau. You can do it that way, or you can just take this whole part, L DI/dt, and look at the original differential equation that we solved in working the circuit. And in that differential equation, we had L DI/dt is equal to, see this right here? We could just put V0 minus IR. So that way works as well. So if I wanted to do that, I can put I out in front, which is going to be equal to, I'll write P battery again. This is going to be I, which is 1/2 of 0.3333 amps times L, which is 240 decimal point millihenries. And then I'm going to multiply that by DI/dt. Or actually, no, we can use, let's go ahead and do the way that your book did. It gives the same answer either way. I actually tried both of them, believe it or not. So what I'm going to do is go ahead and do the I as 1/2 this, and then I'm going to do the V0 minus IR. So I'll write this up here. This will be V0 minus IR, because we see that L DI/dt is in fact V0 minus IR. So this is in fact going to be 20.0 volts minus 1/2 of 0.3333 amps times 60 ohms. And I'll put this as a square bracket. And that should work out. It's so funny that somebody ran over my damn mailbox. All right, so let's see, 0.5 times 0.3333 times, now I'm going to use parentheses just to be safe, 20 minus 0.5 times 0.3333 times 60. Close parentheses. And that gives me 1.667. Actually, that one should be 7, I guess. 1.667. And that's the 1 extra sig fig, and that's the watts.
Why is there a 1/2 right at this front?
Actually, I'm glad you mentioned that, because I was just looking at this answer. It didn't come out to what it was supposed to be. I actually should have used 1/2 in this one as well. Because remember, the question I'm asking you is for the power when the current was actually equal to 1/2 I max. So that 1/2 is supposed to be in there. In fact, this should be 3.333 for that answer for part E. So let me go ahead and change that real quick. Everybody see this right here? That was I max, the 0.3333, but we're supposed to be working this for the battery when it's at the time, the 2.772 milliseconds, and that was the time at which the current was half that. So I'm going to take and erase this, and of course make it 0.5 times 0.3333 times 20. Notice the 0.5 times 20 makes it really easy, because that's just 10 times 0.33. So this is going to be 3.333, and that covers my extra sig fig. I don't like how small that leading 3 is, so I'm going to write it again. This time I'm going to make it ginormous. There you go. So that's the actual power by the battery. And the neat thing about this is you see the power created by the battery is 3.333, but the power being created in the magnetic field is only half of that. So your book actually does a similar example, and then they ask you, where do you think the rest of the power is going? Anybody have an idea on that? It might help you to look at the circuit, for instance.
The resistor?
Exactly. And in fact, if you actually take P equals I squared R, which is another version of power, you can actually say this is going to be 0.3333, or excuse me, that's 3.333. That's the watts. I need half of that, so that's 0.1667 amps squared times 60.0 ohms. And what you'll see is you get, so the current was supposed to be half of 0.333, so I'm just going to double check that. 0.3333 times 0.5, that gives me the 1.6666 whatever. So now I'm going to multiply, I'm going to square that and multiply it by the 60. And lo and behold, you get 1.667 watts, which is exactly the remaining amount. So if you add those two wattages, the watt for the battery and the watt for the resistor, together, you'll get the total wattage that the battery is putting out. Okay, so yeah, you're exactly right. It went into the resistor. Any questions on that one? Nada? All right, it's getting kind of dark over here. Let me turn my light on real quick. Okay, so no questions, right? All right, so that brings me to the next part. So we've done basically an LR circuit. That's a circuit with just a inductor and a resistor. What we need to do now is LRC circuit is what we're ultimately shooting for. But I'm going to start off by looking at a LC circuit. Okay, so let's consider an LC circuit. With an LC circuit, in this case, you basically are going to imagine that you have a capacitor that has been connected to a battery and then allowed it to reach up to the maximum voltage that the battery can supply. So if it's a 20-volt battery, it's going to get the voltage across the capacitor to be 20 volts. And then that, of course, will give you a certain amount of charge, Q0. And that Q0, of course, is given by just C times V, where C is a capacitance. So that's the kind of circuit we're going to have. Let me draw that for you real quick. So what we're looking at here is a capacitor. And that capacitor is, in fact, supposed to be charged. And then that capacitor is going to send out a current because it has a charge, which actually makes positive charges want to leave and go to the negative side. Actually, let me put a switch in that. Whoa, no. So I'll put a switch right here. Okay, and I have a positive side of the capacitor here and a negative side of the capacitor there. And that is a capacitance C and an inductance L. So when the switch is thrown, what's going to happen? Remember, the equation for capacitance is C equals Q over V. So we're going to use that, and we've already used it a couple times already. For instance, we know the voltage drop across the capacitor is V equals Q over C. So what we're going to do is, if I use Kirchhoff's loop rule again, okay, I see that I'm going to go up from the right-hand side of the capacitor. I'm going to go from, let's say, 0 volts to, in fact, V volts, and those V volts will be 1 over C times Q. In other words, just Q over C, but I'm writing that through sort of foretell that we're getting ready to go into a differential equation, and I'm going to put the 1 over C like a coefficient in front of Q. So that's the only reason why I wrote it that way. Now, it's going to, we'll keep walking around the circuit for Kirchhoff's loop rule and following the direction of this arrow, which is the current. Okay, we're going to run into the inductor, and the inductor is going to be a drop in voltage given by L di dt. Now I'm back to where I started from on the circuit. So that's equal to 0. So that's Kirchhoff's loop rule. Now, what we realize is that as the current goes up, it's a result of losing charges in the capacitor. So we know I is going to be equal to negative dq dt as opposed to the normal dq dt. Everybody get that? So in other
Could you
words,
say that again?
so as the current, or excuse me, as the charge on the capacitor Q, as that charge goes down, the actual current is going to go up. So we actually have to have that the current is created at the expense of the charge. So that's why we have an I equals negative dq dt. And I can plug this in now with that. Do you get that now?
Yeah.
Okay. So now I can plug that in, and I'm going to say L d2q over dt squared plus 1 over C times Q is equal to 0, or d2q over dt squared plus 1 over LC times Q is equal to 0. Now, the reason why I put it this way is now it looks more like the harmonic oscillator differential equation when you only had F equals KX. So you had the total force, the summation of forces is equal to mass times acceleration. Mass times acceleration was m d2x over dt squared, and k times x was negative and on the opposite side. So when you pulled the negative kx from the opposite side of the equals, it became m d2x over dt squared plus kx is equal to 0, which we ended up making d2x over dt squared plus k over mx is equal to 0. So you can see it's the identical equation, except now instead of k over m, we have 1 over LC. So you can sort of treat k, you can sort of pretend like we're going to replace k with, say, 1 over C, and we're going to replace m with L. And you can use those same solutions that we had from chapter 14. So what we know the solution is, in fact, is the solution is Q of T is equal to Q0 times cosine omega T plus phi, where phi is just another constant that we can use to align it with the initial conditions. You know, whether the voltage when you first tap, for instance, this thing, is it going to be 0 or is it going to be, you know, a positive voltage? But that's the actual solution of the differential equation. And in fact, if you take the first derivative, you end up getting, obviously, the derivative of sine is cosine. So the derivative of cosine is derivative of sine is cosine. but the derivative of cosine is negative sine. So this is going to become negative omega q0 times cosine of the exact same argument, omega t plus phi. And then that implies that the second derivative is going to be derivative of cosine is negative sine again. Actually, let's see. Yeah, derivative of cosine is negative sine, so that's going to become positive omega squared q0. And this time it turned. Oh, wait a second. I made that. That was supposed to be sine. No wonder I'm getting flopped up. So this right here, when I took the derivative of q, that's supposed to be the derivative of cosine, which is sine, and I didn't write that. So let me fix that now. That's going to be the sine of the same argument. Again, that argument is just omega t plus phi, but I'm saving myself some writing. And that's q0. So now when I take the derivative of that to get the second derivative, I end up getting negative omega squared q0 times the cosine of that same argument again, the argument being omega t plus phi. When I plug that into the differential equation, you might, first off, it might help to realize that this whole quantity right here is just omega squared times q of t. And this one, for instance, isn't like that because it's got a cosine, a sine in there instead of a cosine. So we can't do anything with that, but luckily that's okay because the differential equation only has the second derivative in it, not the first derivative. It's got the second and the 0th derivative actually, which remember the 0th derivative just means the function itself. So when I plug this back into the differential equation, what I see is negative omega squared plus 1 over LC times Q0 cosine of omega t plus phi is equal to 0, but this has to be true for all time. So that's be true at all times t. And the only way that's the case is if that factor out in front is 0. And that means, of course, omega has to be equal to 1 over the square root of L times C. Okay, believe it or not, because omega is equal to 2 pi f, which is also equal to 2 pi over the period, you can see that clearly 1 over the square root of LC must in fact, or the square root of LC must in fact have units of seconds. So I will put this as a little sidebar just to keep track of it. Square root of LC units must be seconds as well. So that's another thing you can try to verify for yourself. But what I want to show you with this is that in fact, you can have, you can do an energy calculation and see something kind of neat. So first off, the energy stored in the magnetic field of an inductor is 1/2 L times I squared, which is going to be 1/2 L. Now we've already calculated that. Remember, I is equal to negative dq dt. And I've got dq dt right here. So this is in fact negative I of t. So I can plug this in and say, okay, well, that's going to be omega squared q0 squared times the sine squared of the argument, which I'll write this time, omega t plus phi. And of course, omega being equal to 1 over the square root of LC, when you square it, you get L over C, or L times C in the bottom. So that's going to calculate, that's going to cancel out that L there. And I will ultimately get 1/2 Q0 squared over C times the sine squared of that argument again. Now I'm going to calculate the energy stored in the electric field, which is 1/2 CV squared. Okay. Well, V, if you remember from your equation in the top left, C equals Q over V. V is actually equal to Q over C. So all I have to do is take the Q and divide it by C. So this is going to become 1/2 C times, I'm going to remind you of this right here. V is equal to Q of T over C. So all I have to do now is take the Q of T and square it and divide it by C squared. So when I do that, I'm going to say Q0. Oops, I should probably write it back in blue again. So I'm going to say Q0 squared over C squared times cosine squared omega T plus phi. You can see that that actually cancels out one of the C's. So I end up getting 1/2 Q0 squared over C times the cosine squared of the same argument. Everybody follow that? So the total energy turns out to be UE plus UB. Notice this one is an ideal circuit that doesn't have any resistance, so that we're not anticipating any energy there. So if you remember the last problem, we had some energy loss. In this case, we don't have that. So it really is truly a fictional setup. But I think you can see immediately what comes from that is we're going to have Q0 squared over 2C times sine squared plus cosine squared, which is obviously equal to 1. So we end up getting, in fact, that this is just 1/2 Q0 squared over C is the total energy. So that's, just one thing you can use to calculate the energy of a circuit that is a LC circuit. But the big thing to see here is actually look at what happens with the energy in general. Ooh, excuse me. Let's make it right here. I really should have used my drawing tools to make that a smoother line. Okay, that's not too bad now. All right. So if I plot the energy in the magnetic field, for instance, what I see is the energy in the magnetic field is actually going to be the one that goes like cosine. So I will say it's going to go like this, 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 and then that's going to go back down here and here. Ooh. I'm sorry for my phone ringing. It's a pain in my butt too. Okay, so that's the energy in the, that's the cosine one. So that's the energy in the electric field. Meanwhile, the energy in the magnetic field, I'll do in red, and that one's going to be more like a sine curve, and it's sine squared, of course. So it's going to go like this. So you can see the energy is just sloshing back and forth between the magnetic field and the electric field, which is sort of like when we talked about a pendulum, which can be modeled by just, a kid on a swing set. The energy is at a maximum when the kid has swung all the way up. I say the energy is a maximum. The potential energy of the kid is a maximum when he swung to his highest position. So that's when mg times h is the energy, because the 1/2 mv squared has v equals 0. But then as he reaches that peak, the gravitational force starts to pull him down, 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 speeding him up, speeding him up, speeding it up, speeding it up. And then when he gets to the very bottom, the gravitational force is straight down, the tension force is straight up. They cancel each other out, and you've got no more forces. At that instant, it's reached its max speed, and therefore the entirety of the energy is in kinetic energy of the form 1/2 mv squared, while the potential energy is in the form of mg times 0. So that's what's happening here. You can see that the blue is at a maximum when the red is at a 0, and then the red is at a maximum when the blue is at a 0. And in fact, you get an oscillatory circuit. So if it wasn't for losing energy to resistance, you could actually have a completely oscillatory circuit. Now, that's just how they behave. The rest of the chapter goes into an LRC circuit, and I'll show you what that is. But the main results there is that there's a term that turns out just like resistance. Ohm's law says V equals IR. Well, it turns out if you look at just an inductor, say, well, let's just start off with the LRC circuit. So what I'm going to do is I'm going to draw an LRC circuit. Well, I don't have much time. I'm going to draw an LRC circuit. There's a switch right here. Okay. And then in my LRC circuit, I'm going to say run into a capacitor of capacitance C. And then I'm going to run into a resistance R. And then I'm going to run into an inductor of inductance L. Okay, it turns out with that differential equation, if you start out, of course, with the capacitor charged, then that'll act like an energy source. And in fact, you can have, again, 1/C times Q minus IR minus L di dt is equal to 0. And using I, which again is going to be negative dq dt, you end up getting, well, I'll cut to the chase and say you end up getting d2q over dt squared plus r over L dq dt plus 1/LC times Q is equal to 0. By the way, if you don't have one of those parts, like if you don't have an inductor, you can just leave off, or you can let L equal 0 and stuff like that. Of course, you see where L will be a problem, but you can configure that afterwards. But basically, this just looks like chapter 14 for a damped harmonic oscillator. So this is like chapter 14. And in fact, what we find is Q of T is actually equal to Q0 times e to the negative R over 2L times T times the cosine of omega prime T plus phi, where omega prime turns out to be the square root of 1/LC minus R squared over 4L squared. And this presents a few different cases. For instance, it presents the case of R squared being less than 4L over C. And that's the part called underdamped. There's a case where R squared is equal to 4L over C. that's called critically damped. And then there's a case where R squared is greater than 4L over C. Sorry, I should make that clear. That's a C. Okay. And that one's called overdamped. And you can look at those solutions either from chapter 14 or from this chapter. I don't consider that part that important because we've already covered it in chapter 14, but that is basically how it behaves. The big thing is if I put an actual power source in there, an AC source, I can compensate for the exponential loss that you see in this little factor right here. I can compensate for that by putting in an AC source. And in fact, if we do that with just a resistor, you get obviously basically just R, or V equals IR, and therefore you can see that the I equals dq dt is going to be basically negative omega. Well, I mean, the main thing is you're going to get rid of that exponential, but it's going to be a negative omega q0 sine of omega t plus phi. And then the V is equal to I times R. So that's going to be negative omega Q times R times the sine. So you see the V and I are in phase. What do I mean by in phase? That means the peaks line up with the peaks and the troughs line up with the troughs and the zeros line up with the zeros, unlike this graph down here at the bottom where the peaks line up with the troughs. Okay, so that's what happens with the resistor. When you actually look at what happens with an inductor, you're again going to have an AC source, and you're going to have basically using current I is equal to I0 times cosine omega t. In other words, let's forget about what we used there. I was just using an example. This is what I'm going to call AC current. Okay. Well, L, or let's say V is equal to negative L di dt. And that becomes negative L times derivative of cosine is, of course, negative sine. So that makes that a positive. And then I'm going to get omega times I0 times sine omega t like that. Okay. Well, you can see that, in fact, using some trig identities, basically what you see is the expression I told you before was ELI, the Iceman. What we see here is that this voltage is in fact, let's say this way, I0 times omega L times cosine of omega t plus pi over 2. In other words, you can use an identity to see that. And not only that, instead of V equals IR, this becomes V is equal to I0 times omega L. And in fact, we define this to be the inductive reactance. So V is equal to I times omega, or excuse me, let's write it the right way, times XL, where XL is defined to be omega times L, which can also be written as 2 pi F times L. And by the way, XL has units of ohms.
How did the sine turn to a cosine?
When you take the derivative, because you see that I is cosine omega t, the derivative of cosine is negative sine. And actually this one you weren't supposed to take, sorry about that. This one you weren't supposed to take the negative. So let me fix that real quick too. You weren't supposed to take the negative here because we're actually getting a power source, the AC. We don't have to lose charge on the capacitor for it. So this in fact becomes, that part right there becomes a negative again. And that becomes a negative, or excuse me, that becomes a positive, because the identity that we use to get from sine of omega t to cosine of omega t plus pi over 2 required that actual negative. So that's how we found that. And what we see is clearly the voltage is leading the current because it's got that plus pi over 2. When you do the exact same thing for this with a capacitor, you see, of course, C equals Q over V implies that Q, and also Q, by the way, you see that V is equal to Q over C, and Q is equal to the integral of I dt. Using that I, you're actually going to get basically V is equal to I0, and then it's going to be 1 over omega C times cosine of omega t minus pi over 2. In other words, when you do all the work, you're going to get that this one's behind it, and that's where the Iceman comes in, whereas this one is where the ELI comes in. And in fact, you see that this right here is going to be a XC, a capacitive reactance. So that should be enough for you guys to get to make some sense of the rest of the chapter. I'm going to cover some more on Tuesday, I guess, or at least I'll put some videos up over the weekend to cover this. But of course, I've read about 2 minutes long, so you guys are of course free to go. I will wait for the last person to ask me any questions before I leave, and I appreciate you guys coming. So thank you very much, and have a good, safe weekend.
Sir, I just had a grade question.
Yes.
I was wondering if you moved all the tests for.
Well, let me check. I think I fixed everything, but there's always a probability that I'm remembering something I did for one of my other classes. So we'll check that. Yes, so I did discover there was a wrong test 4, and it looks like I might have did it backwards from looking at the grade book. Let me double check, because I labeled it wrong one, and I thought I'd figured out that that was in fact the wrong one, and that it was going to stay in the imported items category instead of the one that counted as grades. But now it's looking like I got it backwards. So let me look at this. So it's not in homework, so that's a good sign. Everything I have in homework is accurate. Okay, so the online tests, no, I in fact have the wrong one in online tests. So let me flip that real quick for you in real time, so you'll be able to see the right results. And what I'll have to do is I'll have to take the 1 or 2 students that took the quote unquote right one. I'll move their scores to here, and I'm going to take this students or this score and put it in an imported assignment so it don't count. Okay, so now I'm going to rename this guy. Instead of test 4 27.8, I'm going to say oops. So that's the new name of that. So now it should be more accurate. Thank you for catching that, Christina. I didn't even check it. I just did it because I discovered what I thought needed to be done to correct it. And I never even went back to see that the grade book was consistent with that, which clearly it wasn't. So I'm going to now take the word wrong one out of that one, And in fact, I only had like one student do that other version, which for starters, I don't even know how 2 versions came up, but that was the problem. So I've now just called that one regular test 4. And I just got to move one student's grade over, and I do not think it's yours, but I wanted to check to make sure. Okay, so I got a higher one and the right one here. Oh, this student's grade needs to change, so I'm going to change it to a 100. And this student's grade went down, and this student's grade went up, and that student's grade went up. So I'll leave that. So I had to change 2 students' grade. None of them were yours, but you were having basically a non-done test, a 0 that you that it might have been calculating as a 0 for test 4. You should now have that no longer showing as a 0 for test 4 because it was a test you didn't have to do, and of course didn't do. So now the grade should look better.
Yeah. Now I have an imported assignment at 10%.
Well, there should be 0% on the imported. I will double check that, but yeah, the 10%, I can't even remember anything being 10%. I think 5% was conceptual questions, but I'll double check. The imported is not supposed to have any weight whatsoever.
Oh, okay. Maybe it, because I think it's the practice test for
Gotcha.
the respondus. I didn't actually do it. I just like, it doesn't count towards anything, right?
Right.
The respondus practice test.
No, not the respondus practice test. That shouldn't count as anything. The other practice test only count as extra credit, but so yeah, that should be that.
Okay. So, okay.
All right. Have a good one.
Thank you. You too.
So I'm going to look at that other grade. Anybody else here? I have John. Do you have a question, John?
No, I was just interested in what she was asking.
Gotcha. Yeah, it's always exciting to find that your grade's improving just because your instructor was a goober. So that's nice. So I'm looking at conceptual, that's at 5%. Online test is at 10%. Homework's at 20%. Proctored test is 45. That's right. And so it looks like everything else is good. Oh, the practice midterm multiple times. Yeah, that should be there. That's in the right spot. Yep, everything should be good now.
Yeah, my test 4 seems to be correct, so that's good.
Yeah, actually, was yours one that I just changed? I'm looking at that now.
I don't know, but my
so
test 4 is at 100, so I'm happy.
Yeah, exactly. Yeah, let me see. Oh, no, you were not one that I had to switch, but yeah, you just did that well anyways.
Yeah.
All right. Well, have a good one, John, and have a nice weekend.
Right.
And I will see you next week. Keep an eye on your email. Like I said, I might post some videos to further explain chapter 30. That might help you. And I'm going to try to make them in smaller clumps instead. You know, a lot of my videos are just full hour and 20-minute lectures, or in some cases, they're literally like 3.5 hours because they were from summer classes. But obviously, that's not the best way to use a video because most students aren't going to watch the whole thing. So anyways, keep an eye out for my email, and you have a good weekend.
All right, you too.
Bye-bye.